573. That is the number of active National Weather Service alerts across the United States right now, at this exact moment. Not this week, not today, right now, tonight, while you are watching this. 4 tornado watches are running simultaneously across 6 states. A blizzard warning is active on the other side of the very same storm. Tornado warnings are dropping between 10 p.m. and midnight, while millions of people are asleep with no idea what is moving toward them in the dark. And here's the part that should genuinely unsettle you. This is only round 1. Stay with me until the end of this video, because what comes next is worse. Subscribe and follow along, because this story is not finished. The storm system tearing across 6 states tonight is still moving. The models tracking round 2 are still running. The Arctic reversal building behind all of this is still coming. And when the next development lands, this channel breaks it down first and in plain language. You will want to be here for that. Now, let's get into it. Picture this. It is after 10 o'clock at night across the central United States. Most people have already gone to bed. The kids are asleep. The dog is on the couch. Someone left the television on in the other room. And outside, in the dark, the sky is doing something that meteorologists are watching with the kind of focused, quiet intensity that should make all of us a little nervous. At 4:45 in the morning, Coordinated Universal Time on March 7th, 2026, which translates to roughly 10:45 at night Central Time, the National Weather Service had 573 active alerts spread across the United States. 573. Now, the NWS issues alerts constantly. That is not unusual on its own. But on this particular night, buried inside that number were 4 active tornado watches, a severe thunderstorm watch, and a cascade of tornado and severe thunderstorm warnings dropping in real time across 6 states. That is not a routine evening. That is an atmospheric system in the middle of losing its temper. The Storm Prediction Center, the branch of the National Weather Service that watches for organized severe weather on a national scale, had issued 4 separate tornado watch boxes. They go by the designations Watch Number 16, 18, 19, and 20. Those 4 watches covered enormous geographic areas. We are talking about Kansas, Missouri, Iowa, Arkansas, Oklahoma, and Illinois, all simultaneously wrapped inside these watch boxes, which signal that conditions are favorable for tornado formation across dozens of counties at once. A single tornado watch covering 1 state gets your attention. 4 watches running at the same time across the Central Plains. That tells you the atmosphere is not playing around. Now here is something worth understanding about what a watch means versus a warning, because the distinction matters more than most people realize. A tornado watch means the conditions are right for tornadoes to develop. Think of it as a loaded gun. A tornado warning means a tornado has either been confirmed on the ground or radar is showing rotation so clear and organized that forecasters are willing to stake lives on the assumption one is imminent. On this night, both watches and warnings were active simultaneously. The gun was loaded and it was already firing. The storms themselves were moving fast. Shockingly fast, actually. Storm motion was being tracked at between 40 and 55 miles per hour to the northeast. That might not sound dramatic until you start doing the math. At 55 miles per hour, a storm can cross an entire county in less than 30 minutes. A tornado warning that gets issued with a 12-minute lead time, which is already considered good, shrinks to something almost meaningless when the storm is moving at highway speeds. You have 12 minutes, and then the window is gone. And on this particular night, those warnings were being issued between 10 p.m. and midnight Central Time, which means millions of people across 6 states were asleep when these storms started dropping out of the sky. The Storm Prediction Center had already flagged this region under what is called an enhanced risk. that is level 3 out of 5 on the severe weather scale. Level 3 is not the top, but it represents high confidence. When the SPC puts you at enhanced, they are not guessing. They are telling you something organized and dangerous is coming, and the meteorological evidence to support that conclusion is solid. Flash flooding was simultaneously being reported in parts of Missouri. A blizzard warning, yes, a blizzard warning, was active on the other side of the same storm system. We will get to that, because it is one of the most remarkable details of this entire event. But here is the thread I want you to hold onto right now. This outbreak, this 573 alert, 4 tornado watch, 6-state overnight monster, was only round 1. The models were already showing another severe weather event forming. And behind that, a full atmospheric reversal that could bring Arctic cold and a significant snowstorm crashing into the Northeast. This was not the end of something. This was the opening chapter, and one tornado warning in particular had meteorologists watching their radar screens like hawks in the dark. At 10:36 p.m. Central Standard Time, the National Weather Service office in Springfield, Missouri, issued a tornado warning. The county in question was Newton County. The city in the crosshairs was Neosho. Now, Neosho is not a major metropolitan area. It is a small city in the southwest corner of Missouri, the kind of place where the streets go quiet after 9, and most people have no idea that a meteorologist in Springfield is staring at a radar return that is making their stomach drop. On this night, Doppler radar had detected rotation inside a severe thunderstorm moving toward them, and the warning language did not mince words. The warning stated that a tornado was possible. It flagged quarter-size hail and damaging winds. It described hazards including flying debris, destroyed mobile homes, and roof and window damage. The severity classification attached to that warning was extreme. The urgency classification was immediate. Those are not routine words. In the taxonomy of NWS warning language, extreme and immediate represent the top tier of threat. They are the words forecasters use when they want you to understand that this is not a watch from the window situation. This is a get to your safe room situation. The storm was moving northeast at approximately 40 miles per hour. That means it was not drifting, it was charging. And understanding why a storm moves that fast requires us to back up and talk about what was happening structurally in the atmosphere above the central United States that night. Radar signatures on this system suggested something meteorologists call a supercell embedded within a line of storms. A supercell is a specific type of thunderstorm with a rotating updraft, called a mesocyclone, that makes it uniquely capable of producing tornadoes, large hail, and damaging winds. They are the most dangerous thunderstorm structure on Earth. The challenge on this particular night was that this supercell was embedded inside a larger line of storms. And that matters enormously because of what it means for detection and for human behavior. During the daytime, a supercell often has a distinct visual signature. That ominous rotating wall cloud, the greenish sky, the stillness that experienced storm chasers know to respect. At night, you cannot see any of that. The storm is invisible. You cannot look out your window and assess whether you need to act. The only tool that cuts through that darkness and tells forecasters what is actually happening inside those clouds is Doppler radar. Radar velocity data measures wind motion toward and away from the radar antenna simultaneously. When forecasters see opposing velocities, wind moving toward the radar on one side, wind moving away on the other, in a tight, compact pattern inside a storm, that is the rotational signature of a mesocyclone. That is the fingerprint of a potentially tornadic storm. And on this night, that fingerprint was showing up in Newton County while most of the county was asleep. The window for residents to respond was measured in minutes, not hours. There is another atmospheric phenomenon that made this particular overnight event more dangerous, and it goes by the name of the low-level jet stream. The low-level jet is a ribbon of fast-moving air that flows northward from the Gulf of Mexico at relatively low altitudes, typically between 2,000 and 5,000 feet above the ground. It transports warm, moist air into the plains and Midwest, and it has a habit of strengthening after sunset. As the surface cools at night, the friction that normally slows this jet down decreases, and the wind speeds ramp up. More moisture gets pumped in. More energy gets delivered to already active storms. This overnight intensification is well understood by meteorologists, and it is one of the reasons nighttime severe weather events in Tornado Alley are treated with extra caution. The atmosphere was essentially getting a second wind at exactly the wrong time. One cell near Neosho, one warning, one narrow window of time. But this was not an isolated storm. This was one node in a web of severe weather stretching across hundreds of miles of American heartland, and the full scope of what the maps were showing that night was something else entirely. Pull back the camera for a moment and look at the full picture. Severe weather on the night of March 7th was not concentrated in one county or one state. It was distributed across a geographic area so large that trying to describe it with specific cities starts to feel inadequate. Kansas, Missouri, Oklahoma, Arkansas, Illinois, and Iowa were all simultaneously inside the active severe weather environment. Some reports extended into Mississippi as well. This was a multi-state atmospheric event of a scale more typical of late spring than early March. In Kansas, storms were tracking northeast near Perry Lake at approximately 55 miles per hour. The hazards being cited included 60-mile-per-hour winds and penny-size hail. Towns in the path included Lawrence, Oskaloosa, Eudora, and Perry, communities spread across northeastern Kansas that had little warning time given how rapidly the storms were moving. 60-mile-per-hour straight-line winds, for context, can down large trees, knock out power lines, flip unsecured structures, and cause significant damage to buildings that are not built to withstand that kind of lateral force. These are not gentle thunderstorm winds. These are winds at the lower threshold of hurricane force gusts. Oklahoma was generating its own round of warnings. Reports were coming in of quarter-size hail near Alderson and 60-mile-per-hour wind gusts across Cherokee, Delaware, Mays, and Ottawa counties. Quarter-size hail is roughly the diameter of a United States quarter coin, about 24 millimeters. That size of hail, falling from a severe thunderstorm at terminal velocity, can shatter car windows, strip the bark from trees, damage roofing, and cause real injury to any person caught outside without shelter. These are not statistics. These are conditions that were occurring in real time across multiple counties in eastern Oklahoma while the region slept. Further east, Mississippi was not spared. Half-dollar-size hail was reported near Como and Senatobia. Half-dollar hail is significantly larger, approaching 2 inches in diameter, and represents a storm with considerable energy in its updraft. The fact that hail of that size was falling in Mississippi tells you how far the atmospheric energy was extending across the southeastern corridor. Severe thunderstorm warnings across the region were citing consistent hazard language: roof damage, siding loss, tree damage, and vehicle impacts. What unifies all of these events, Kansas, Oklahoma, Missouri, Mississippi, is the storm motion vector, consistently northeast at 35 to 55 miles per hour. That uniformity tells a story. It says that the upper-level wind pattern's steering. These storms was strong, organized, and pointed in a single direction. Meteorologists call this a high-energy synoptic setup. Synoptic means large scale. We are talking about the behavior of the atmosphere across thousands of square miles, not just local conditions. When you have a synoptic scale setup driving severe weather, you do not get 1 or 2 isolated storms. You get a coordinated, widespread event where the entire atmospheric column across a region is primed to produce violent weather. What is also notable about this particular outbreak is its timing on the calendar. early March is not traditional tornado season. The climatological peak for tornado activity in the central United States falls in May and June for most of the plains. March can certainly produce tornadoes. History is full of examples, but a multi-state, multi-watch event in the first week of March is not something you see every year. The atmosphere was running ahead of schedule in a way that should raise questions. Questions about what conditions were in place to make this possible. And those questions lead directly to something even more unsettling about what was happening on the other side of this storm. Because at the same moment, these tornadic supercells were firing across the southern plains and Midwest, another part of the country was buried under snow and experiencing blizzard conditions inside the very same weather system. Let us talk about timing, because this might be the single most dangerous variable in this entire event. Tornado warnings were being issued between 10 p.m. and midnight Central Standard Time. Think about what that means practically. The average adult in the central United States goes to bed somewhere between 9:30 and 11 p.m. Children go to bed earlier. Elderly residents, statistically speaking, are often the least likely to have multiple redundant warning systems in place. At 10:36 p.m., when that warning dropped for Newton County, a significant portion of the population in the warned area was asleep. Not half asleep. Asleep. This is not a new problem, but it is one that kills people with a regularity that should disturb us. Research on tornado fatalities consistently shows that nighttime tornadoes carry a substantially higher mortality rate than daytime events of comparable intensity. The reasons are compounded and overlapping. People are asleep. The storm is invisible. Outdoor warning sirens, which are designed to alert people who are already outside, not people inside their homes, are often inaudible through insulated walls, closed windows, and background noise. Weather radios, which are the most reliable indoor warning tool, are not universally owned or used. And mobile phone wireless emergency alerts, while increasingly effective, can arrive minutes after a warning is issued, minutes that may not exist when a storm is moving at 50 miles per hour. History has taught this lesson in brutal terms. The 2011 Super Outbreak, the largest tornado outbreak ever recorded, with 360 tornadoes in 2 days, produced its most catastrophic single event during daylight hours in Tuscaloosa and Birmingham, Alabama. But the overnight phases of that outbreak also killed people. The 2020 Easter Sunday outbreak struck at night across the Deep South, and in December of 2021, a tornado tore through Mayfield, Kentucky after midnight, killing dozens of people who were inside a candle factory on the night shift. A reminder that nighttime tornado risk is not limited to people who are sleeping. It simply means the darkness removed every visual cue that might otherwise motivate someone to act. The embedded supercell structure of this particular outbreak added another layer of difficulty. Classic textbook supercells, the isolated rotating towers that form on the open plains in the afternoon, often have visual signatures that trained observers can recognize even at moderate distances. But when a supercell is embedded inside a squall line or a broken line of storms, it loses that visual distinctiveness. The broader storm system masks it. The only reliable way to identify it is through radar velocity analysis, which requires either a professional meteorologist watching in real time or a well-educated consumer who knows what they are looking at on a radar app. Most people, woken from sleep by their phone buzzing with an emergency alert at 10:45 p.m., are not running radar analysis. They are trying to figure out if they are awake enough to move. The speed of these storms collapsed the margin for error further. When a storm is moving at 55 miles per hour and a warning is issued with a 10-minute lead time, the geography of threat shrinks to something almost geometric. You have roughly 10 miles between you and the hazard when the alert arrives. If you are asleep and your phone takes a minute to wake you up, and you spend another minute figuring out what the alert says and where to go, you have 8 minutes. That is 8 minutes to get yourself and your family to an interior room, ideally below ground level, For people without basements, which is common across parts of the plains and Midwest due to soil conditions, that margin becomes even more uncomfortable. This is the midnight tornado problem. It is not a hypothetical. It was happening in real time across 6 states on this particular night. But here's the question that the midnight tornado problem should send you toward. Why was the atmosphere so volatile in early March? Why was this happening at all? To understand that, you have to look at the engine behind the whole system, the parent storm that was driving every tornado watch, every flash flood warning, every blizzard condition simultaneously. And that storm had a name. Well, a designation. It was centered over Kansas. Every major severe weather outbreak in the central United States has a driver, a source of atmospheric organization so powerful that it forces the entire regional atmosphere to respond to its presence. On the night of March 7th, that driver was a mid-latitude cyclone centered over Kansas. This is the class of storm system responsible for most of the significant weather events that affect the continental United States throughout the year. Not a tropical cyclone, not a blizzard in isolation, but a sprawling, organized low-pressure system that functions like an enormous atmospheric vacuum cleaner, pulling air inward and upward in ways that produce dramatically different weather depending on which side of the system you are standing on. Mid-latitude cyclones work through contrast. They exist because the atmosphere is trying to balance an enormous temperature difference. In this case, the difference between warm, moist air being pulled northward from the Gulf of Mexico and cold, dry Arctic air pressing southward behind the system. The low-pressure center acts as the pivot point. To the southeast of the low, in what meteorologists call the warm sector, you get the conditions that spawn severe thunderstorms: warmth, humidity, instability, and wind shear. To the northwest of the low, in the cold sector, you get winter, snow, ice, and on this particular night, blizzard conditions. One storm. 2 completely different worlds on either side of it. To understand why tornadoes formed inside this system, you need those 3 ingredients that meteorologists have identified as the fundamental requirements for tornado development. The first is instability, which is essentially a measure of how much the atmosphere wants to overturn, how eager the air near the surface is to rise rapidly when given a trigger. Instability is provided by warmth and moisture near the ground combined with cold air aloft. The second ingredient is moisture, specifically the supply of warm, humid air from the Gulf, which feeds the thunderstorms with energy and keeps the atmosphere from drying out. And the third is wind shear, the change in wind speed and direction with altitude. Wind shear is what gives thunderstorm updrafts their rotation. Without shear, you get ordinary thunderstorms. With strong shear, updrafts begin to spin, and supercells and tornadoes become possible. On this night, all 3 ingredients were present and interacting at the same time. The low-level jet was pumping Gulf moisture northward as it strengthened after sunset. Upper-level winds from the jet stream aloft were providing the shear that organized the storm structures. And the temperature contrast between the warm sector and the approaching cold front created exactly the kind of instability that made the atmosphere want to erupt. The timing, overnight, during the peak of low-level jet activity, amplified everything. This was not a case of a couple of thunderstorms happening to produce a brief rotation. This was a well-organized, atmospheric ingredient-aligned severe weather event, running on precisely the right fuel at precisely the wrong time of night. And yet, and this is the part that genuinely stretches comprehension, at the same moment all of this tornado activity was occurring in the warm sector, less than a few hundred miles to the northwest. Inside the very same parent storm system, a blizzard warning was in effect. Snow was falling. Roads were dangerous for entirely different reasons. One storm. Tornado warnings in Missouri. Blizzard warnings somewhere else. If that does not qualify as weather whiplash, nothing does. Here's a sentence that sounds like it cannot possibly be true. On the night of March 7th, 2026, 1 blizzard warning, 50 winter weather advisories, and 3 winter storm warnings were simultaneously active alongside 4 tornado watches. Read that again. Blizzard conditions and tornado conditions were occurring inside the same weather event, at the same time, in the same country. This is not a quirk or an anomaly. This is what meteorologists have come to call weather whiplash, and it is one of the most visually dramatic expressions of what a powerful mid-latitude cyclone can do to a continent-scale atmosphere. The mechanics of this are actually straightforward once you understand the structure of the storm. In a mature mid-latitude cyclone, the warm and cold sectors are separated by frontal boundaries, lines in the atmosphere where contrasting air masses collide. On the southeastern side of the low, the warm, moist Gulf air creates the environment for severe thunderstorms and tornadoes. On the northwestern side, cold Arctic air dominates, and precipitation falls as snow rather than rain. The temperature gradient across the entire system can exceed 50 degrees Fahrenheit over a horizontal distance of just a few hundred miles. You could drive across that gradient in an afternoon. On one end, green grass, warm air, sirens wailing. On the other end, whiteout conditions, impassable roads, and entirely different survival concerns. This kind of simultaneous weather contrast has appeared before in powerful historical systems. In April of 1975, a significant storm system produced tornadoes in parts of the plains and Midwest while bringing heavy snow to other regions. The so-called storm of the century. In March of 1993, created blizzard conditions from Florida to Canada, while simultaneously producing severe thunderstorms and tornadoes in Florida. These are extreme cases, but they are not unprecedented. What makes them remarkable every time they occur is the sheer energy they represent. The temperature contrast across the system is not just a meteorological curiosity. It is the fuel. The bigger the difference, the more violently the atmosphere tries to resolve it, and the more dangerous the weather on both sides of that battle line becomes. The fact that a blizzard and 4 tornado watches coexisted on the same weather map on the same night is a direct expression of how much energy was stored in the atmosphere over the central United States that evening. Think of it this way. The atmosphere operates like a heat engine, always working to balance temperature differences between warm and cold air masses. When those differences are large, the engine runs hard. When the engine runs hard, it produces violent weather on both ends of the spectrum simultaneously. The blizzard was not a separate event from the tornado outbreak. They were both symptoms of the same underlying cause, an atmosphere under extraordinary stress, trying to find balance across an enormous temperature divide. But that raises an obvious question. Why was there such an extreme temperature contrast in the first place in early March? Why was the warm sector so warm? The answer to that points towards something happening across the eastern United States in the days surrounding this event that was genuinely abnormal. A temperature anomaly so large it was functioning almost like an accelerant poured onto an already volatile atmospheric fire. In the days surrounding the March 7th outbreak, temperatures across the eastern and central United States were running between 20 and 40 degrees Fahrenheit above normal for early March. Let that number settle for a moment. 20 to 40 degrees above normal is not a mild warm spell. That is not spring arriving a week or two early. That is the atmosphere presenting temperatures that should belong to May or even June, inserted into the first week of March. In many locations, this would be the warmest temperature ever recorded for that particular calendar date. The warm air mass sitting over the region was not just unusual, it was anomalous in the most technical sense of the word. Early March, historically, still behaves like winter across much of the central United States. The ground is cold. The air is cold. Nighttime temperatures frequently drop below freezing. The Gulf of Mexico is not yet pumping moisture north at its summer level rate. Severe thunderstorm season in the classic tornado alley sense has not yet opened for business. Except on this particular week in 2026, none of those seasonal expectations were being honored. The atmosphere was running months ahead of where it should have been. Warm air matters for severe weather for a reason that is almost intuitive once it is explained. Atmospheric instability, that tendency for surface air to rise rapidly when triggered, scales with the temperature difference between the warm, humid air near the surface and the cooler air higher in the atmosphere. When surface temperatures are 20 to 40 degrees warmer than normal for the time of year, that difference is amplified. The atmosphere becomes more eager to overturn. Thunderstorm updrafts become more powerful. Storm tops punch higher into the troposphere. The energy available to any storm that gets going is substantially larger than it would be during a normal early March setup. Meteorologists sometimes describe this kind of situation as false spring instability, the atmosphere producing dangerous convective energy at a time of year when the atmospheric ingredients are not supposed to be aligned for it. The Gulf of Mexico was contributing to this problem as well. Ocean water temperatures in the Gulf were running above average, meaning the moisture supply being fed into the storm system was unusually robust. Warm ocean water evaporates more readily, loading the low-level atmosphere with more water vapor, which is both a fuel source for thunderstorms and a carrier of latent heat energy that gets released explosively when thunderstorm updrafts form. This is the mechanism by which the Gulf of Mexico functions as the moisture engine for tornado outbreaks, and on this particular night, that engine was running at a level more consistent with late spring than the first week of March. When you take 20 to 40 degree temperature anomalies, add an unusually active Gulf moisture supply, stir in the wind shear provided by a powerful mid-latitude cyclone, and drop the whole thing on a region of 6 states in the middle of the night, the result is the event we have been describing. But here is what should genuinely concern you going forward. All of that energy does not simply dissipate. The atmospheric pattern that produced this outbreak was not a one-night event. The same system, as it moved through and evolved, was generating other hazards simultaneously, and one of them was completely different in character from the tornado threat, but no less dangerous. While tornado warnings were being issued across Missouri and the surrounding states, a separate and equally urgent hazard was developing in the southwestern corner of Missouri at the same time. Flash flooding was confirmed in a cluster of counties: Barton, Dade, Jasper, and Newton. Rainfall totals in the 1 to 3 inch range were accumulating over short time periods, and flash flood warnings had been issued by the National Weather Service with immediate urgency classification. Emergency management officials were confirming flooding conditions on the ground. This was not a forecast. It was already happening. Flash flooding develops through a process called training thunderstorms, and it is worth understanding because it is one of the more treacherous weather phenomena that gets overshadowed by the dramatic imagery of tornadoes. When thunderstorms form within a flow pattern where successive cells move repeatedly over the same geographic area, like train cars on a track, rainfall accumulates in that area far faster than the ground can absorb it. The individual storm cells may not each produce exceptional rainfall totals, but if 3, 4, or 5 of them move through the same location in succession, the cumulative total can trigger dangerous flooding within an hour or two. The conditions present on this night were favorable for exactly that kind of training pattern. The storm motion was consistently northeast, but the source region, the area where new storms were firing, remained to the southwest. As long as that remained the case, new cells kept moving through the same corridors. The warm, moist Gulf air feeding the storms also increased what meteorologists call rainfall efficiency, the percentage of water vapor in an updraft that actually falls as precipitation rather than evaporating before reaching the ground. High moisture content means high rainfall efficiency, more rain per storm, more rain per hour. Flash flooding at night carries risks that are distinct from daytime flooding. Drivers encounter flooded road sections without adequate visual warning. Water levels rise rapidly in low-lying areas where people may be sleeping with no awareness of what is happening outdoors. Streams and creeks that appear harmless in the afternoon can become raging channels within minutes of a heavy rain event upstream. The National Weather Service phrase that has been repeated for years, "Turn around, don't drown," exists because a disproportionate number of flood fatalities involve vehicles entering flooded roads that the driver misjudged or simply did not see in time. On a dark March night in southwest Missouri, with tornado warnings active 50 miles to the east, flash flooding was quietly adding another layer of danger to an already overwhelmed landscape. Between the tornado warnings, the flash flooding, the multi-state severe thunderstorm activity, and the blizzard conditions on the system's cold side, this single overnight event was producing, simultaneously, nearly every category of dangerous weather that the North American atmosphere is capable of generating. That alone is extraordinary. But here is what the meteorological community was watching beyond the immediate crisis, because the atmosphere was already drafting the next chapter while this one was still being written. Somewhere in the middle of tracking 573 active alerts and 4 simultaneous tornado watches, the Storm Prediction Center quietly did something that tells you everything about how the meteorological community viewed the situation. They issued a Day 5 slight risk outlook for a new area of the central and southern United States, covering a corridor from Texas to Illinois, valid for the period from Tuesday through Thursday of the following week. Day 5. 5 days out. The SPC does not issue Day 5 products casually. Issuing a slight risk on Day 5 means that the confidence in a developing severe weather setup is high enough, and the model signals are consistent enough that forecasters are willing to put a formal product on the map nearly a week before the event. A slight risk is level 2 out of 5 on the SPC's scale. It is not the top. But a Day 5 slight risk for a corridor stretching from Texas to Illinois is the meteorological equivalent of a doctor saying, "I want to see you again next week, and I want you to be prepared for what the tests might show." It means something is coming. The atmosphere is not resetting. It is cycling. The setup driving round 2 shares structural similarities with the setup that produced round 1. The same general atmospheric pattern, the jet stream configuration, the moisture feed from the Gulf, the interaction between warm and cold air masses was expected to persist. In fact, the term that climatologists and long-range forecasters use for this kind of sustained pattern is a severe weather highway. When the jet stream locks into a configuration that repeatedly steers storm systems through the same geographic corridor, outbreak after outbreak can occur in the same general region over periods of days or even weeks. The plains and Midwest were, in the first week of March 2026, sitting directly underneath that highway. The Tuesday through Thursday window carried a particular concern that echoed the problem with round 1: nighttime storm potential. Model guidance was suggesting that the most active phases of the developing severe weather could again occur during evening and overnight hours. Meteorologists were watching the timing closely because the difference between a severe weather event that develops at 2 p.m. and one that develops at 2 a.m. is the difference between a manageable situation and a potentially catastrophic one, even if the meteorological ingredients are identical. Same atmosphere, same tornado risk, completely different human outcome based on whether the sun is up. The fire weather component behind the cold front that would follow this second system was also drawing attention. As the cold front swept through, the combination of low humidity, dry air, and strong winds created conditions favorable for rapid fire spread across parts of the southern and central plains. Fire weather risk is often the footnote to severe weather events in this region, but it represents a third category of danger, separate from tornadoes and flooding, but equally capable of causing catastrophic damage in a short time. The atmosphere in the days following round 1 was not settling down. It was shifting modes, moving from severe thunderstorms to potential fire weather to the setup for the next severe outbreak, cycling through hazards the way a machine cycles through functions. And beyond round 2, something larger was already appearing on the models. Something that represented not just another storm, but a fundamental shift in the atmospheric pattern itself. A reversal so dramatic that forecasters were using the word Arctic in the same week that tornado watches had been active across 6 states. Here is how dramatically the atmosphere was about to change. Within the same 10 to 14 day window that contained this tornado outbreak and the developing round 2 severe weather event, long-range models were signaling an Arctic air intrusion into the central and eastern United States that would push temperatures from 20 to 40 degrees above normal, all the way to 20 to 30 degrees below normal in some locations. That is a temperature swing of 50, 60, even 70 degrees Fahrenheit over the span of roughly a week. You would go from conditions warm enough to generate tornado watches in early March to conditions cold enough to shatter temperature records on the cold side within days of each other. That is not weather variability. That is the atmosphere having an identity crisis. The meteorological driver behind this reversal is a concept called ridge west, trough east, a description of the large-scale pressure pattern across North America. When a ridge of high pressure builds over the western United States, it forces the jet stream to buckle southward on the eastern side, carving out a cold air trough that dips deep into the lower 48 states. This configuration, when it locks in, acts like a door held open in winter. Arctic air from Canada pours southward through that open door and spreads across the plains, the Midwest, and eventually the eastern seaboard. The same configuration that, on its warm side, helped fuel the tornado outbreak, was expected to swing its cold side like a pendulum in the opposite direction within days. The European model, widely regarded as one of the most accurate global weather forecast systems in the world, was showing a significant precipitation event associated with this Arctic intrusion in the form of a potential snowstorm targeting the northeastern United States. The numbers being suggested were not trivial. Model guidance was indicating potential snowfall accumulations of 10 to 15 inches in some areas. 10 to 15 inches of snow in the northeastern United States is a major storm by any standard, the kind of event that closes airports, shuts down transit systems, and makes news for days afterward. The GFS model, the American counterpart, was showing a weaker system, meaning there was real disagreement in the guidance about exactly how much snow would fall and where. But the signal for a significant Arctic event, including meaningful snowfall in the Northeast, was present in both model systems. The disagreement was about intensity, not about whether something was coming. This is the full atmospheric arc of the pattern that defined March 2026's first and second weeks. You begin with temperatures 20 to 40 degrees above normal. Tornado outbreak across 6 states. Flash flooding in Missouri. Blizzard conditions on the cold side. 573 NWS alerts active simultaneously. Then, round 2 building for later in the week across the Texas to Illinois corridor. Then, an Arctic reversal dropping temperatures by 50 to 70 degrees over a matter of days. Then, a potential 10 to 15 inch snowstorm targeting the Northeast. One atmospheric pattern. Multiple catastrophic chapters, written back to back inside a single calendar month. Step back even further, and what you are looking at is not just a series of weather events. You are looking at something that atmospheric scientists are increasingly concerned about as a pattern of behavior: the volatility of the March atmospheric transition period in a climate system that has been accumulating anomalous energy for years. March is the hinge month. It is the point on the calendar where winter and spring compete for dominance across the northern hemisphere, and the battles they fight are conducted in the form of weather. But when the combatants are mismatched, when the spring warmth arriving is exceptionally far ahead of schedule, when the Gulf of Mexico is unusually warm, When the Arctic still has cold air to export, but finds it colliding with abnormally warm air masses at mid-latitudes, those battles become more violent. The temperature anomalies that fueled this outbreak did not arrive out of nowhere. In the weeks leading up to March 7th, a series of above-normal temperature events had been building across the central and eastern United States, creating what some forecasters were describing as an extended period of anomalous warmth for the season. The ground had not frozen to its normal winter depth in some areas. Soil moisture was elevated. Vegetation in parts of the southern plains was already responding to the warmth. The atmosphere above all of this was carrying energy that, under normal early March conditions, simply should not have been there. Now, the relationship between long-term climate trends and any specific weather event is a topic that requires precision. Meteorologists are careful, rightly so, to distinguish between climate, the long-term average behavior of the atmosphere, and weather, which is what happens on any given day. Attributing a single outbreak to a single cause is an oversimplification, but documenting patterns, noting that early March tornado outbreaks of this scale are becoming more detectable in the record, that temperature anomalies preceding severe weather events are showing up with greater frequency and magnitude. That is legitimate science, and it is science that forecasters are actively engaged in. What is certain is that the atmospheric ingredients present during the first week of March 2026 were aligned in a way that produced historic scale severe weather across a 6-state region, followed by an Arctic reversal of comparable magnitude, all within a single 2-week window. Whether you want to explain that through pure atmospheric dynamics or through the broader lens of a climate system showing increasing variance in its behavior, the practical reality is the same. The weather on this night was dangerous. The weather coming next was dangerous for entirely different reasons. And the people in the path of all of it had, in many cases, less warning than they deserved. Think about what the atmosphere just put into a single 2-week window in March 2026. A multi-state tornado outbreak at midnight. 4 tornado watches active simultaneously. Flash flooding in Missouri. A simultaneous blizzard warning on the other side of the same storm. 573 National Weather Service alerts active at once. A second severe weather event already signaled by the Storm Prediction Center for Tuesday through Thursday. Fire weather conditions in the wake of the cold front. And then an Arctic air mass plunging southward with enough force to produce a potential 10 to 15-inch snowstorm in the northeast, arriving within days of a week that saw tornado watches across the plains. The meteorological community tracked all of this in real time with extraordinary precision. The NWS offices that issued those warnings, Springfield, Missouri, issuing the Newton County tornado warning at 10:36 p.m., the SPC issuing 4 watch boxes simultaneously, the offices tracking flash flooding in southwest Missouri. These forecasters were doing exactly the job they are trained to do, and they were doing it well. The science of tornado prediction has improved dramatically over the past several decades. Warning lead times have increased. Radar technology has become more sensitive. Model guidance has become more accurate at longer lead times, which is why the SPC was able to post a Day 5 slight risk for Round 2 before Round 1 was even finished. But the science of delivery, of getting warnings to sleeping people in time for those warnings to matter, is still a work in progress. Outdoor sirens were not designed for indoor populations. Weather radio penetration is incomplete, and the gap between a meteorologist issuing a tornado warning with an extreme severity classification and a person in a mobile home in Newton County actually acting on that warning in the 12 minutes before the storm arrives is a gap filled with friction, uncertainty, and sometimes fatal outcomes. The technology that builds forecasts has outpaced the technology that converts those forecasts into protected human lives. The story of the March 7th, 2026 tornado outbreak is, at its core, a story about contrast. The contrast between blizzard and tornado on the same weather map. The contrast between 20 to 40 degrees above normal temperatures and the Arctic air that followed. The contrast between the precision of modern meteorology and the stubborn human reality of sleeping through warnings. The contrast between how well we understand the atmosphere and how poorly we have solved the last-mile problem of actually reaching the people who are in its path. Every time a system like this tracks across the central United States, it is a test. A test of the warning systems, the infrastructure, the preparedness of the communities in the path. And every time one of these systems tracks through in the middle of the night, the test gets harder. The atmosphere does not schedule its most dangerous moments for daylight hours and calm weather. It does not give advance notice beyond what the models can extract from the physics of fluid dynamics and thermodynamics. It simply does what it does. And what it was doing on the night of March 7th, 2026, across 6 states in the dark, was asking a question that the United States Tornado Warning System has been trying to answer for decades. How do you protect people from something they cannot see, arriving faster than they can react while they are asleep? We have made progress. We have not solved it. And somewhere in the models, another storm is already forming, carrying the same question into next week. The atmosphere does not wait for us to finish asking. It just keeps moving, northeast at 55 miles per hour, into the dark.